Welcome to week 11 lecture 3 on probability theory with actuarial applications. In today's class we are going to discuss how to compute the second moment of the severity claims, and in particular we can also compute variance of y. So let us see how to do it and understand why this is important. I have already established the need to do this in previous lecture, but let us again understand. So in the last class we actually figured out how to find a general formula for variance. Once we have this, then it was basically very simple. First we figured out what is expected value of n, which was easy and we have done it in week 3. Then we figured out how to find variance of n, which is the frequency variance, again easy, which was done in week 3. Then the next thing was expected value of y, severity mean. We solved in week 10 how to find all those severities with deductibles, limits and layer policies. Now comes variance of y, which is the severity variance. How will you compute that? So in order to compute this variance, you essentially look at the formula for variance, which is variance of y equal to expected value of y square minus expected value of y the whole square, where you already know what is expected value of y. So the second part is already known to you. So what you do not know is this part, that is the missing part is only expected value of y squared. How will you calculate? And this is the second moment of per claim payout. So let us again go back to Poisson shortcut and see how you will do it in that case. So when you are having compound Poisson shortcut or compound Poisson model, you already know from the previous lecture it is lambda times expected value of y squared. So the implication of that is to find the variance of compound Poisson portfolio. The only difficult thing that we need to calculate is second moment of our per claim payout, expected value of y squared. So this lecture is dedicated to finding expected value of y square for policies with deductibles and limits. So let us go one by one. So naturally what will be our key tool here when we were deriving deductibles and policy limits? The LOTUS, right, the law of unconscious statistician. So that will help us. So let us use that and try to understand how we will derive expected value of y square for them. So the tool is LOTUS again, and for the first moment we used it like this: expected value of y is equal to expected value of gx, and it is integral 0 to infinity gx fx dx. Now I am asking you to compute expected value of y squared, so which essentially means it is a gx squared. So I will use the LOTUS again. I will treat this as another random variable z, and you can integrate over this z. So in particular what you are integrating is integral over 0 to infinity gx square fxx dx. Here the assumption is this will never take negative values, right. So that is why the integral over 0 to infinity suffices. So let us get into the game and understand first what happens with deductibles. Expected value of y square for deductible. So a policy which has a deductible D, payout y is max of 0 comma x minus d, right. So what was our tool LOTUS when we looked at y is equal to gx? We looked at the payout function which was something like this: if x is less than or equal to d, you pay nothing; if x is equal to greater than d, you pay x minus d. So now what we are asking is what is expected value of y squared. For that you define the random variable y square. What will be a typical value? This, wherever it is 0, it will be 0 there. The kink will be at d, and therefore it will happen, this will go at a quadratic rate x minus d square, okay. So how will you handle this particular random variable? What does the LOTUS say? Let us try to investigate that. So, you are essentially calling for expected value of y squared. So, which is integral from 0 to infinity y square f(x)(x). So, now I will write in terms of gx. So, it is going to be gx squared f(x)(x) dx. But what is gx square? You have already seen this. This is integral and the kink is at level d. So, it remains at level d. So, I can easily split this integral into 0 to d something gx square f(x)(x) dx plus integral from d to infinity f(x)(x) dx. What will be written here, because this value is going to be 0 here. So, it will be 0 times this and this will be x minus d squared times this, correct, and therefore, this will automatically vanish and I get expected value of y square to be equal to integral d to infinity x minus d squared f(x)(x) dx. That is the formula that we have. So, this is the second moment of the excess loss. So, the kink is at d, you have split the formula and you have essentially calculated the second moment of excess loss if you are able to solve this integral. Okay. So, that is expected value of y square when policy was deductible. What if you look at the policy from the framework of policy limits? So, expected value of y square for a limit policy. So, your policy limit is say u, then your payout is minimum of x comma u. Then naturally you will look at the payout function as a step process or step function, which will be x if x is less than u if x is greater than or equal to u. Now, when you look at y square, this becomes x square and u square. Can I do similar thing for with lotus? Yes, of course I can do. So, that is expected value of y squared will be equal to integral from 0 to infinity gx squared f(x) dx. What is the natural kink here? At level u. So, I will say integral from 0 to u, something is there f(x) dx plus integral from u to infinity f(x) dx, and now what will be this? This will be simply integral 0 to u. So, in this range from 0 to u, this is x squared. So, I have x squared here, and for x greater than or equal to u, I have u squared. However, this first integral will remain as it is, there is no question about it. So, it is x square f(x) dx, but the second integral, if you look at the integrand, that u square is a constant. So, it will be thrown out and this is integral u to infinity f(x) dx, but this is similar to what we did with policy limits, right. So, instead of u minus d, we have u squared. So, we can easily see this particular thing which is within the integral and the integral itself as survivor function s x of u and multiplied with u square, the other part will continue to be there, correct. So, this is our formula for second moment of limited loss. Kink is at u, important points to brush up is kink is at u, you can compute expected value of y square using that split at the kink, and the second part becomes the survivor function multiplied by u square and the first part remains as integrals. So, with all these things we have understood how to compute the second moment for the loss distribution or insurer payout. That is what we have considered in today's class. Let us solve one problem for exponential deductible and understand it from the shortcut perspective that is available for exponentials. So, I have exponential distribution. Exponential distributions have memoryless property, which will come very handy in this case also. So, x follows exponential lambda, it has a deductible d. So, for first d dollars we are not going to pay anything. So, x minus d will inevitably come and you have to find expected value of y squared. So, you look at the per payment logic. Expected value of y square is actually equal to expected value of y square given y is greater than 0 into probability of y greater than 0. Now, but what is y square? Y square is x minus d squared given x is greater than d, right, and that essentially means I am looking at exponential random variable again and the second moment of exponential random variable. That means I can easily compute these probabilities using memoryless property and I can tweak this expectation to be the expectation of original random variable. So, let us do those steps one by one. First, can I compute probability of x greater than d? Of course, it is a survival function of exponential random variable. So, it becomes e raised to minus lambda d, no problem. Second step, I want to look at the expected value of x minus d square when x is greater than d. Naturally, this has to do with memoryless property, whether I start from d or start from 0, the distribution is going to be the same. So, by memoryless property, x minus d square given x is greater than d will have same distribution as x squared. Okay. Therefore, expected value of x minus d square given x greater than d is same as expected value of x square. Now, you see the beauty, how simple it is. So, do I know what is expected value of x square? Yes, I can easily compute because what I know is variance of x is going to be 1 by lambda squared, right. So, variance of x is going to be 1 by lambda square. Expected value of x is going to be 1 by lambda. But what I want is expected value of x squared, right, which is nothing but sum of these two quantities, not exactly these two quantities, it is variance of x plus expected value of x the whole squared. So, which essentially means it is 1 by lambda square plus 1 by lambda square gives me 2 by lambda square. So, I know expected value of x square is going to be 2 by lambda square. Then do I know this probability? Yes, I do know because I know this quantity, I know this quantity is this. So, multiplication of these two quantities will give me the final answer. So, I have shown expected value of x square is actually 2 by lambda square. I have to multiply 2 by lambda square by e raised to minus lambda d and I got the answer or expected value of y square. How good or how simple is this? This is our exponential deductible shortcut. Now, whatever we have done for exponential, we can generalize it to a general context, though in exponential the calculations were very simple. So, if I want to find variance of S for a compound Poisson model with deductible d and severity claim exponential 1 by mu, that means the mean value of exponential is mu. So, what I will do? Very simple, I know variance of S is lambda times expected value of y squared, nothing, I simply need to calculate expected value of y squared. So, our tool will be to find expected value of y square. So, I will just simply go based on x following exponential, I know expected value of x is mu, variance of x is mu squared. So, expected value of x squared will be 2 mu squared, nothing great, right. And now, because I have this expected value of y squared, I will simply push this into probability of x greater than d is e raised to minus d by mu, because this exponential 1 by mu was there. So, lambda is 1 by mu, so it is e raised to minus lambda d, that lambda becomes 1 by mu. Then expected value of y square is 2 mu square times e raised to minus d by mu. So, I have a formula for variance of a deductible of total aggregate claim to be equal to lambda times 2 mu square e raised to minus d by mu, where this lambda is coming from Poisson lambda, 1 by mu is the rate parameter of exponential distribution. So, let us now summarize what we have done so far. We have figured out how to find this missing piece, expected value of y square, which is needed for calculation of variance of S. In particular, we have designed a toolkit which is our moments of payout toolkit. For deductible d, expected value of y is integral d to infinity x minus d fxx dx. Expected value of y square is d to infinity x minus d square fxx dx. If it is a policy with limits and the limit is u, expected value of y is, the second term is u times survival function of at u, and the first term is integral 0 to u x fx dx. If I am looking at the squared moment, then the second term will be u square times survival function, and the first term will be x square times fxx dx integrated from 0 to u. Okay. So, we have covered mean and variance for our total aggregate loss. We have all the formulas. Now, we will run full scale master drill that takes us from n and x to all the way up to expected value of S and variance of S. That is what is the goal of our next lecture. Okay. Thank you.